In these examples of curve sketching, I'm going to use calculus to find maximums, minimums, and points of inflection. Now, this is the first function that I'm going to look at in factored form. This is the first derivative. We use that to find maximums and minimums. And here's the second derivative. And I've got these in factored form because what I'm going to do is I'm going to make a chart, and I'm going to look at the x values, first of all, where the first derivative is 0, and that's at 0 and 3. I've got those marked here. And the second derivative at 0 and plus 2. And what I'm going to do is I'm going to fill in this chart. I've got the x values where the first derivative is 0 and where the second derivative is 0. And make sure these are in the order that they come on the x-axis. Now, because the second derivative is 0 and the first is not, I know for certain that I have a point of inflection here. At x equal to 3, because the first derivative is 0 and the second derivative is positive, meaning it's curving upward, I know that I have a minimum. So here's a point of inflection at -2. I put the 2 back in here to get the y value. Point of inflection at 2, -16. A minimum at 3, -27. Now, over here I had a bit of a problem because when the first and second derivative come up 0, we're not really sure whether there's a maximum, minimum, or point of inflection. So what I did was I checked the first derivative on either side of 0. I could put in, say, a -1 and a +1. Don't go too far here, you can't go past that number. I found out that the first derivative was negative, meaning that the curve was decreasing. So it was coming down, flattening out, and then coming down again, meaning we had a point of inflection at 0, 0. Putting all this together, this is what it looks like. You see, I knew the derivative was negative. I was coming down, flattened out, came down, hit the point of inflection here at 2, -16, and I changed from being concave down to concave up, and that accounts for the minimum here at 3, -27. The crossing point here, I just got back from the function itself. You can see that the zeros are 0 and 4. I don't usually list the y values here because I want to keep this as simple as possible. I just want to look at the first derivative and the second derivative when I'm doing this analysis. The y values will show up down here when I write these particular points. Now, the second example is a little more complicated. Notice the denominator of this is never 0, so we don't have to worry about any vertical asymptotes. However, because the power on the bottom is higher than on the top, we have a horizontal asymptote of y equals 0. Once again, I have the first derivative and the second derivative. The first derivative becomes 0 when x is plus or minus √2. It's a little bit awkward, but if x squared is 2, then x is plus or minus √2. And here's the second derivative factored. 3 values here, 0 and plus or minus √6. So the numbers are a little awkward, but this is I'm drawing this just like the the x-axis, go from the negatives into the positives. And I've written down all of the zeros here. The first derivative, as I mentioned, is 0 at the √2's, and the second derivative at the √6's and the 0. Also checked out the value of the second derivative at -√2 and +√2. Found out that we're concave up here, creating a minimum, and concave down there, creating a maximum. Now, these points aren't the simplest to graph. They're not that bad to figure out the y value because, for example, if you put √6 in here, you get √6 over 6 plus 2, which is just √6 over 8. And I guess you could convert these into decimals to get an idea of what's going on here. But putting it all together, this is what this graph would look like. The maximum is here, the minimum is here, and of course we have a point of inflection between them. You always expect to find a point of inflection between a minimum and a maximum. The other points of inflection on the outside enable us to recognize this horizontal asymptote of y equals 0. Because you see, if you're concave down here, at some point you have to change the way you're bending so that you become concave up, and the x-axis becomes an asymptote. The other thing you can notice here, maybe you noticed it right at the beginning, if you replace the x with a negative x, all you get here is negative x over, this will still be x squared plus 2. This is what we call an odd function, because when you replace the x with minus x, you get the negative of the original, and you can see the symmetry about the origin that we have here. My third and last example for this is another rational function. You see this time we have a vertical asymptote at x equal to 1. I've mentioned that here. And the oblique asymptote, we arrive at that by expanding the top into x squared plus 2x plus 1 and dividing this in. And the quotient you get is the oblique asymptote. And you get that because the power of the top is 1 higher than the power on the bottom. So we've got a couple of asymptotes. Here's your first derivative. It's equal to 0 at negative 1 and 3. I've got those marked here, negative 1 and 3. It's also undefined at 1. That's important to put that in your list too. If the derivatives are 0 or undefined, we want to list them here. A second derivative is never 0, so we don't have to worry about points of inflection here. But we do use the second derivative to decide whether it's positive or negative. We use that to figure out whether we have a maximum at negative 1 or a minimum at 3. Once again, I put these x values back into the original to get the y value. So putting all of this together, the first thing I do is I draw my asymptotes. Here's x equal to 1. Here's y equals x plus 3. That should really be coming through at a 45-degree angle, but you see I had to squeeze the numbers on the y-axis in order to reach this 8. But it's very simple to put this together because having a minimum here just slides us between the two asymptotes, and having a maximum over here, once again at negative 1, 0, just slide them in between the two asymptotes. So I would suggest when you make your chart here, don't worry about the y value. Just get a clear analysis of y prime and y double prime, and do the analysis from there. Then you can always list the y value when you mark your max, min, or inflection points.